In this video, we're going to say a little bit more about the homology of RPN for general n. So let's recall RPN is this quotient space. Where we take an n sphere and we identify u with minus u. Okay, and so so we proved some time ago that RP1 is homeomorphic to S1. Okay, even though it's a quotient of S1, it's also homeomorphic to S1, and so obviously the homology of RP1 is just the usual thing. And we also showed that the next one, homology of RP2, which has got a z and then a z mod 2 and then zeros thereafter. And we're not going to do a complete calculation of the homology of RPN, not here, but we're going to at least say some basic stuff. I'm going to say that for n at least 3, well, firstly, h1 of RPN is still the same z mod 2. Okay, it's the same as we had for RP2. And we're also going to need to know that these homology groups stop eventually, and they stop above the dimension. Now, for k bigger than n, you've got no homology group. Okay, and this is it's a general fact that we're not going to prove in this course, but when you've got a space that's n-dimensional in some appropriate sense, then you don't have any homology for k bigger than n. Okay, so all the proof we'll use it's going to be possible to write RPN as a union of two open sets U and V, where U is going to be homotopy equivalent to RPN minus 1, V contractible, and U intersect V homotopy equivalent to Sn minus 1. Okay, so I think what we'll do is we're going to do the homological argument first, just kind of assuming these things. So we'll prove the proposition, assuming this. And then prove the claims about these U and V's. Okay, so we're assuming n's at least 3, and RPN is U union V, U homotopy equivalent to RPN minus 1, and V is homotopy equivalent to a point, and U intersect V homotopy equivalent to Sn minus 1. We're going to claim that H1 RPN is Z mod 2, and HK and we're going to prove this. We're proving this inductively. the corresponding facts for n minus 1, so that we're okay, so we're assuming that firstly that h1 of rpn minus 1 is a z mod 2, and that hk rpn minus 1 is trivial when k is bigger than n minus 1. Okay, so so now let's have a look at the Meyer-Vittori sequence. So we're looking at, we're interested here in H1 of RPN. Okay, so we get H1U plus H1V, and here H1U intersect V. Yep. And then we get a delta down here. Well, actually, yeah, so truncated Meyer-Vittori sequence like this. Now here we've got H1 U intersect V, which is H1 Sn minus 1, which is 0, because we're assuming that n's at least 3. Okay, and then here you've got your H1U and H1V. Well, V is contractible, so there's no H1V, and then H1U, well, U is homotopy equivalent to RPN minus 1, so we've got the same as the so that's a Z mod 2 by our induction hypothesis. And exactness implies that this is an isomorphism. I'm calling this okay, because we've got a 0 here and a 0 there. That forces this to be an isomorphism. And so we see that H1 RPN is Z mod 2. And now if we've got k bigger than n, okay, so then here we've got our hk of RPN here. And then we've got our delta down here going to hk minus 1 of the Sn minus 1. Okay, now here k is bigger than n, k minus 1 is bigger than n minus 1. So we're out of the range where this can have any homology. So we've got a 0 there. And then coming in from here, you've got your HKU plus HKV. Okay, and then of course this is HK RPN minus 1. And HK of a point, because U is homotopy equivalent to RPN minus 1, and V is equivalent to a point. Now, again, by our induction hypothesis, this HK of RPN minus 1 is 0, provided K is bigger than N minus 1, and actually got one extra space here. K is actually bigger than N, so this group is 0, and of course HK of the point is also 0. So here we've got this group here sandwiched between a 0 and a 0. So we see that HK-RPN is trivial. And, we could actually extract rather more information from this Meyer-Vittori sequence if we made some more effort to understand exactly what the maps are, but we won't do that here. Okay, so our Meyer-Vittori argument was based on the idea that we've got these open sets U and V with properties as described. So we need to check that works. Okay, so let's recall here what RPN looks like. so it's a quotient of Sn. Sn. Okay, so Sn is the stuff is the unit sphere in r to the n plus 1, which we're going to think of as r to the n plus r. Okay, so this is, we can think of this as the set of pairs x, y and r to the n cross r. I think we're going to call this yz, actually. Let's call this yz, where square norm of y plus z squared is 1. Okay, and then so we're going to have our u, which we'll put u tilde this is going to be a set of those yz in Sn, where z is going to be not, well, let's say, well, y is non-zero. For y to be non-zero, that by this equation here, that's the same saying as z is not equal to plus or minus 1. Or if you like, this is Sn with kind of north and south poles removed. And whereas our v okay, so yeah, so this is basically, in other words, this is kind of Sn with the equator removed. And so if we put v plus as a set of yz, where z is strictly positive, and v minus is a set of pairs yz, where z is negative. Okay, so this is like your upper hemisphere and your lower hemisphere, and v tilde is the union of those. So let's let pi from Sn onto Rpn be the projection. And u is pi of u tilde, v is pi of v tilde. Okay, so these are the sets that we need to deal with. Okay, let's think about v first. So remember, v is v tilde is okay. So yeah, v tilde consists of it's what we get by removing the equator. We've got the upper hemisphere and the lower hemisphere, and so each point in v plus kind of gets glued go to a unique point in v minus. So pi is going to give us a homeomorphism from v plus to the space v. Remember, v was the image of v tilde in RPN. So every point in v has precisely two pre-images in Sn, one in the upper hemisphere, one in the lower hemisphere. So pi is giving us a bijection from the open upper hemisphere to v. Yeah, so yeah, so our v is it's a v plus, which is But v plus, that's just a set of things of the form y and then square root of 1 minus norm y squared, where this is any point in the open-end ball. You've got a point in the open-end ball, then you just set z to be the square root to force this to be true. So v is also homomorphic to the open-end ball, therefore contractible. Okay, and that was one of the things that we needed. We wanted v to be contractible. Okay, so that just so now we need to understand about u and u intersect v. Okay, so now so we look at the intersection u tilde intersect v tilde. Remember, that's the set of those y, z in Sn. Y is non-zero and z is also not zero. But this is kind of v tilde with so v tilde. We say v tilde. That means we're kind of forcing y to be non-zero, and then we're just removing the poles. Okay. Okay. So this one, of course, was in our v plus, and this one was in our lower hemisphere v minus. And so okay, so yeah, we're just removing this pair of points, one in v plus and one in v minus, and after we push everything down into RPN, what we're doing is we're just taking our original v and removing a single point. So we find that u intersect v is homeomorphic to, well, remember our v plus was just the open ball in Rn, and then we just remove a single point. But this thing here, you take the open ball of radius, open ball in Rn, remove a point, what you get is just going to be homotopy equivalent to Sn minus 1. You've seen that sort of argument a bunch of times. Okay, so that deals with u intersect v, but we still need to understand about u. Okay, so let's recall this u tilde. That's the set of yz in Sn for which y is non-zero. So we're going to define a map I tilde from Sn minus 1 to u tilde. It's just sending y to y comma 0. And we're going to define R tilde in the opposite direction. Okay, so we've got a pair yz in u tilde. Y is non-zero, so it's legitimate to divide by the norm of y to get a unit vector. So it's clear that R tilde composed with I tilde is just the identity on Sn minus 1. The composite the other way around is not the identity, but it's homotopic to the identity. Okay, so we just multiply our the z coordinate by t, and then we have to divide by this square root to make it back into a unit vector to ensure it lies in Sn. Okay, so of course it's legitimate to divide by this because y is non-zero, so this is always at least as large as norm y squared, and and because y is non-zero, this first coordinate here is also going to be non-zero, so we're always staying within u tilde. Okay. So the point about all these tilde maps is that they're all compatible with our equivalence relation. I tilde of minus y is minus I tilde y. R tilde minus y minus z is minus R tilde yz. H tilde t minus yz is minus h tilde of t comma yz. So these are all compatible with our equivalence relations. So we get induced maps I from quotient of Rpn of this, which is Rpn minus 1, to the quotient of u tilde by plus or minus 1, which is what we were just, that's our open set u. And these satisfy, that this is going, R composed with I is going to be the identity, I composed with R is going to be homotopic to the identity via this H. So that gives us this I is a homotopy equivalence. So right there, this so this is proving that our U is homotopy equivalent to Rpn minus 1, and we previously showed that V was contractible and that U intersect V was homotopy equivalent to Sn minus 1. So now we know what the homotopy types of all these things are. We know their homology, and by the argument that we explained earlier with the Meyer-Vittorius sequence, we can deduce the facts that we claimed about the homology of Rpn. Okay, so that's as much as we're going to prove about the homology of Rpn for the moment, but I will state the full answer. So a convenient way to state the answer is to introduce this chain complex Pn. Okay, so in a chain complex like this, with a copy of Z in every degree from 0 up to n, and the differentials are going to alternate between 0 and 2. Okay, so that's the definition of the chain complex Pn, and then so it's a proposition which I'm not going to prove, but I'm going to state that the homology of Rpn is isomorphic to the homology of this complex Pn. Okay. So you can spell this out a bit more explicitly, but it just requires sort of separating cases and things. So the more explicit answer depends on whether we've got our n is even or odd. So let's look at the even case. Okay, so this is for the even case, you get z if k is 0, z mod 2 if k is odd, and k is less than 2m, and 0 otherwise. And if you look at the odd case, in the odd case, it turns out you actually have two z's. Right? If you remember, yeah, well, we discussed RP1. I mean, RP1 is just a circle that's got two z's. You've got k is 0 and k is 2m plus 1. You get z's, and you get some z mod 2's as well. And then you get some zeros. Okay, yeah. If you so it's just it's an easy exercise to check that this describes the homology groups of this complex Pn. You just have to be a little bit careful about separating different cases. But then, yeah, and then the claim is that that's actually the homology of Rpn for general A.